Hello, hello.
Hello, sir.
Good morning, sir.
Good morning. Okay, sir.
Yes, sir. Your voice is clear, sir.
Hello.
Hello. Good morning. Good morning.
Good morning to all.
Good morning. I think somebody's voice is echoing. You have two devices nearby. You have to switch off. And already YouTube streaming has started. So I think we'll go off on audio and mute your audio and off your video. So at exactly when I stop my screen share, 10 o'clock, Ms. Shaija can start.
Yes. Am I audible?
Yeah. I think your voice is echoing.
Yes.
Yes, Shaija, your voice.
So otherwise, everybody will go on mute now. Ms. Shaija, can you check again your voice?
Yes. Now it's okay.
No.
Echoing.
No, echo is coming.
Echo is coming.
Now?
Yeah, it's okay, ma'am.
Now it's better. Yeah, it's good. Mr. Santosh, good morning. Can I hear from you? Your voice is okay?
Hello. Good morning.
Yeah, good morning. Thank you. Mr. Kumar, also, I think your audio is good.
Yes, sir. I can hear all of you.
Miss Amna, good morning, ma'am. Miss Amna, you hear us?
Yes,
Yeah,
clear.
yeah. Thank you. So sharp 10 o'clock, we will start, okay? So I'm
Okay.
waiting for Dr. Justice to join. I'll just check if he has joined already.
Yes, sir.
So who will give me green light for welcoming them?
Miss Shaija.
Ma'am, me.
Okay, thank you.
Dr. Justice is online. Can anyone check? Dr. Sudhakar, Mr. Santosh, can we switch off the videos? Thank you. Dr. Justice is in.
Hello.
Yeah, good morning, Dr. Justice.
Yeah, good morning, Prasanna.
Yeah, so it's time. It's time now. Looking for the time. Yeah, we'll be starting within a minute now from now.
Yeah, please.
Thank you, Doctor.
Ang problema ko, yung sa Mark at saka sa ako sa Mac, LLC.
Yes, Ms. Shaija.
Yes.
We will start.
Yes. Good morning, one and all. Myself, Dr. Shaija. Let's start the session with a welcome address by our HOSI team, Ms. Amna Al-Kabi. Before we start the welcome address, a few guidelines to be followed. Kindly keep your audio in mute and video off to avoid any background distractions. Any questions can be entered in the chat box through the presentation. Moderators will be managing the chat functionality. During the last 30 minutes, the forum will be open for discussion. During the time, you can unmute and ask your questions. At the end, feedback regarding the webinar will be posted in the chat box. Kindly answer. Over to you, ma'am.
Hello, everyone, and welcome to today's session of webinar on research and practice in knowledge engineering. I'm Amna, head of IT section. On behalf of IT Research Committee, Shenas College of Technology, I would like to give a warm welcome to our resource speakers, Dr. Justice S. Professor and Head BTech VIT, Chennai, India, and Dr. Hepzibah Mabel, Associate Professor, CSE VIT, Chennai, India, to train our mind to think. As word of Einstein, education is not the learning of fact, but the training of the mind to think. Thank you all for joining. A recorded video will be available later.
Thank you, ma'am. Before we request the resource speaker to start the session, I'd like to introduce them briefly. Dr. Justice S. is a PhD in computer science and specialized in software and knowledge engineering. His research work areas include software metrics, knowledge management, knowledge representation models, design of knowledge base for experts, and so on. The list goes on. So, and he has taught many courses like knowledge representation and reasoning, advanced software engineering, and this list also is too long to be expressed here. He has published 40 plus research articles and 30 plus conference papers, which is indexed in IEEE and Scopus. He has presented his work in Germany, Israel, USA, and many parts in India too. He is presently working in knowledge base creation using K-graphs, machine learning in knowledge base, health and care in ICD-V10, and now about other speaker, Dr. Hepzibah Mabel. She is a PhD in computer science with 15 years of teaching experience and research experience in knowledge representation models. She has taught various courses like advanced Java programming, embedded system designs, and so on. She has also published and presented numerous articles in her research interest. Today, we have the opportunity to listen to them. Now, I kindly request Dr. Justice S. to address the participants. Over to you, sir.
Yes, ma'am. Thank you for the nice introduction. So good morning, everybody. To be happy to be part of this webinar. And I thank Dr. Prasanna for arranging this seminar. And it's a time that we are all remotely connected, virtually working in our homes. And I'm going to take 2 hours of our time for you. And this 2 hours of time is not enough. Actually, this is a 5-hour bootcamp program on knowledge engineering. But we have customized this to just 2 hours session where we'll have some introduction. The agenda is we'll have some introduction about knowledge engineering, and then we'll go on to the video lectures where we'll be playing some 1 hour videos, 1 hour, 2 videos. One will be by me and one will be by Dr. Hepzibah Mabel. And then I'll be presenting some lights on the research and the practice parts and the research that we do in VIT, Chennai. And we'll have the floor for discussion after that, right? So I have to rush it up, all of this stuff within the given 120 minutes. Okay. So I'm sharing my screen. So I hope that I'm clearly audible to you all. So if there's any glitches in the middle, just you can stop me. Okay, so here in Tamil Nadu, no? In Tamil, we used to use this term like arivirka, konjamada arivirka, right? Which means, do you have any sense at all? Do you have knowledge? So this is a common term that we use to talk to our children, like scold our children and our students or some people that we meet on road, sometimes those who do absurd things. Like, do you have sense? Do you have knowledge? That's what it means, which means, do you have the basic sense of thinking? Do you have the basic sense of reasoning, right? So when we talk about our knowledge, it's all about reasoning on moral values. When I say moral value, you need to cross the road. You need to cross the road when the walker's light is green. You need to cross the road on the zebra crossing. You need to drive on the road to the left-hand side in India, right? So these are all moral values, but when you deviate from these values, you used to hear all these sentences like, do you have knowledge, do you have reasoning, etc., right? So more reasoning comes from moral values. Similarly, when we come to computer programming and software systems, it is always like reasoning. We are making our computer systems to think, reason out based on facts and rules. And that's what we call as knowledge or knowledge-based systems, right? So knowledge engineering and knowledge management systems, these two go hand in hand most of the times, but they are two different verticals where we need to have, where we'll be having different implications in the implementation part of knowledge management system and knowledge engineering or knowledge-based systems. Right. So as far as I know, the earliest paper in knowledge management or knowledge engineering was written in 1980 by a group of research team in Stanford University. And you see these guys at Stanford University are always 20 to 30 years ahead of the rest of the world. Last year, when I was chairing a session in the Indiana Summit in US, there was a professor, I forgot his name. There was a professor who was addressing the audience on this knowledge management. And he was telling like this, see, the research groups and the teams of research professors working in Stanford are always thinking ahead of 20 to 25 years ahead of what the rest of the world is thinking. So they were talking about knowledge management in the 1980s. And 20 years later, in 2001, the patents were filed in the US repository of knowledge management processes, whatever you are seeing here on the screen: knowledge acquisition, representation, reasoning, and you have knowledge sharing, implementation. So all these processes are being patented in the US Patent Office in the early 21st century. And 4 years from there, teams of professors working in UK were talking about acquisition and representation. And in 2006 to 2000, I was doing my PhD, my professor, my supervisor, was part of that UK based project. And we used to get a lot of information. We learned a lot from our professor on the knowledge representation and the reasoning part. So that was a good learning at that time. Now, after 10 years, we are not talking the same representation acquisition model that they were talking 20 years back. We are talking knowledge acquisition, representation, reasoning, implementation at another level, where we have AI involved in, machine learning involved in, IoT involved in, blockchain technology is involved in, and it is all vertical based, domain based. So the processes and the concepts that we are going to discuss today are at that level where we have got many implementation projects and we have got many implementation platforms which are still functioning in our area, right? Which means in our domain of expertise. Okay, so this is the agenda today. We'll be talking about knowledge forms and processes, acquisition and representation. I'll finish in another 15 minutes. And then we'll go to the recorded video on knowledge reasoning and implementation of the knowledge base. And after that, we'll have a discussion on research and practice and the possibilities of research areas in knowledge engineering. Okay, so I have just given the processes one by one. First one, the forms of knowledge. The first form of knowledge is a tacit form of knowledge. Say, for example, I'd say that I know to drive a car. I can talk about driving a car for 3 hours to you. So this knowledge is in my brain, in the human brain. So any form of knowledge that is inside the human brain is called the tacit form of knowledge, and you cannot express it by itself. You don't have an expressive form of the stored knowledge in your brain. So that form is called tacit knowledge form, which cannot be expressed. If you ask me to tell about how to drive a car, I can write steps on it, but that is not actually the knowledge that I have in my head. I know how to switch on the car, and I know how to put on the gears and give the accelerator, and I know how to move a car, but those things cannot be explicitly told, or it cannot be expressed by any medium. One popular medium is lecturing, that I speak to you. This is knowledge transfer. Whatever knowledge I have in my mind, I'm putting into words, and then I'm transferring into the second party or to the third party. So this is one popular means of expressing knowledge that was in the tacit form. Okay, the second form is explicit form. Now, this is all we are concerned about. Explicit form is the knowledge form which could be expressed. So whatever form that I have in my head has to be explicitly expressed in one form or the other. One popular form is told that my lecture can be recorded and it can be processed later. You can listen to it later, or you can convert into transcripts, or you can convert into relational database tables, relations and tables. So it can be on any form which could be expressed in a formal representation model. So all that we are going to talk here about knowledge acquisition, representation, reasoning, all these things are concerned only with the explicit form, not with the tacit form, right? So we have got many challenges and we have got many problems, and we have to have generalization of representation and reasoning. Algorithms are there, and yet algorithms are being discovered to handle explicit form of knowledge. This is very important, and all the organizations, learning organizations and research organizations are working on that part of explicit form of knowledge. Implicit form of knowledge. Now, this is a hidden form of knowledge that is available both in explicit and a tacit form. You will not know until some event will happen and that knowledge would pop out. This is more strange, and this is more what? This is more very much challenging that you talk about explicit, right? You do not know that knowledge is underlying in the explicit form, right? So that is called implicit. Implicitly, it is available, and it can be precipitated only when you have some events or when you have triggered some events to bring that knowledge out. So only when that comes out, you will come to know, okay, this knowledge is available. So that is one challenging form of knowledge. And the last one is hybrid form. This is the new knowledge that you would get out of the reasoning of the explicit form of knowledge, right? I manipulate the explicit form of knowledge. I manipulate even the tacit form of knowledge, and I get new knowledge. This is what we are doing. Every day we learn, right? We learn through studying, through watching videos, through these listening to lectures, and also through experiences. Now, all the new knowledge that you get out of experiences and the learning process are categorized into the hybrid form of knowledge. So these are the most common forms of knowledge, but be aware that there are many types of knowledge, which I'm not going to get into that, because those types of knowledge are always classified, or they are categorized based on the domain of their applications. So that differs from ontology to ontology, or from person to person, or from application to application. So these are the four main forms of knowledge. So those are the definitions. Okay. And the next one is knowledge acquisition. The next process is knowledge acquisition. Most important thing, without this process, the rest of the process cannot function. Right. Now, I don't know how many of you have the habit of reading the newspaper in the morning. They have forgotten those hard copy of the newspapers, like some 10, 15 years back, our parents or our grandparents, or sometimes we ourselves have that kind of habit of reading the newspapers. But today we don't have that. Now, how do we actually read a newspaper? Morning with the coffee, I'll just go through the headlines, first page, second page headlines, third page headlines, and then I go through till the end of the newspaper, and I then throw it away. Then I take my breakfast and I go on with the other works. And when there was a leisure period, leisure time comes in. I'm talking about the non-working hours, not during the working hours, right? So in the leisure time after 10 o'clock or 11 o'clock, I'll take the newspaper back, and then I read the first page, the first headline, and the first a few paragraphs, or just the first paragraph or one or two paragraphs. And when I start to read that, I get involved in that. Sorry, I get involved in that, or that topic may be of importance to me just by reading the first paragraph. If I'm interested in that part of the news, then I'll read the rest of the paragraphs in that given headline, right? If I'm not interested in that headline and in the first paragraph, then I move on to the next news article in the same page. This is called reading. You read the newspaper. If it is of interest to you, you continue reading and you gain knowledge, you discover knowledge. Similarly, I need to write algorithms for acquiring knowledge in this fashion. You call that as content parsing model. Content parse. I parse the content, or I read the content, or I creep through the content, or I walk through the content, right? So usually these algorithms that I have, we have also done some algorithms on knowledge acquisition, like it will read through the contents and identify concepts. We are not entered into knowledge. Okay, so identifying concepts and relating them to the context, and then we say we have found some knowledge. All right. So first thing is you read the content, identify concepts, and then you relate that concepts to the context in which the paragraph is written. And then you put on the relations between these concepts, and you build up a model where you say, this is the knowledge I have got through reading this part of the news article, right? Or through the text. Now, this I'm talking with analogy of the reading the newspaper. Now, this is applicable for structured repository, unstructured repository, or semi-structured repository. Structured repository is kind of, you have the, I'll come to that later. Okay, so we'll have a clear discussion on that later. Right, the second one is knowledge representation. The knowledge that I have got in the previous step, the knowledge acquisition part, needs to be represented in some formal forms so that my computer system will be able to handle that. For example, we have relation database system. So we have relation database queries, structured query language or NoSQL, to query the database and get information from the database tables. So those are the database tables or formal representation of data. Similarly, I need to have a formal representation of knowledge that could be represented to the computer systems. Why? I need to go for reasoning. As I told earlier, reasoning based on facts and rules. So when I can do the reasoning, only when I have a formal representation model of the knowledge that I have acquired, right? So this representation is very important. And this is important because we need to do the reasoning on the acquired knowledge, right? And once that is done, I need to go for the storage. Sorry. Now, data, you take the analogy of the relation database system. You have date type, integer type, text type, and the string type, varchar type. So these are all data types with which you store data into your secondary storage device through your RDBMS. Similarly here, I need to store my knowledge, the knowledge unit that I have obtained in some form into the storage layer, right? We'll be discussing that at the later part of the video. The second part of the video will be talking about storage and retrieval of knowledge. Now, this is usually done using object-oriented or object-relational or object-based storage system, right? And the next one is knowledge sharing. Now, how do I share the knowledge that I have acquired, represented, reasoned out, and that I have in my knowledge base? Now, how do I share that with the environment? And this is a big challenge that has been addressed in various knowledge sharing forums and in research, right? We did a research some time back, some 4 or 5 years back, in this knowledge sharing thing, where we proposed 2 algorithms. One is for lossless knowledge and lossy knowledge. When you share knowledge, there is always going to be a loss. See, I'm going to talk to you for 2 hours, and I'm not delivering whatever I know. All right? Say for example, I'm having 100% of knowledge with me. As I talk for 2 hours to you, I'm going to just share only 60% of knowledge, right? And as you listen, sitting in your place remotely through your mobile phones or in your laptops, you are going to grasp only 25 to 30% of the knowledge. Now, see, imagine there are 70% of knowledge loss in this knowledge sharing techniques, right? So this is one major challenge. Now I'm talking about learning organization, right? So knowledge sharing in learning organization. But when knowledge sharing comes to between knowledge-based systems, that should be lossless knowledge sharing, right? Lossy knowledge sharing is permitted in learning organizations like us, that you work in a remote college and I work in a remote university. Both of us are sharing knowledge. So when learning organizations participate in sharing knowledge, you will be having loss of knowledge. But when you come to communication between 2 knowledge-based systems, knowledge engineering systems, say for example, you take 2 robots. When 2 robots need to communicate between themselves, that knowledge sharing should be lossless. That is very challenging, and there are very large number of research groups working on that area. Very challenging, but if you are interested in that area, maybe you can pick that particular area and work on it. And knowledge generation is that I told you, hybrid knowledge generation from the knowledge that I have already right? And the final thing is applications of knowledge. Now, studying the theory part of the knowledge and just having the theoretical knowledge is not enough in these times of technological advancements. You should know how to apply the knowledge, where to apply the knowledge, and how efficient is your knowledge base going to work in your knowledge base systems, right? You take Facebook, you take Flipkart, you take Amazon, you take Twitter. Now, all these are knowledge-based systems. Implicitly, they are knowledge-based systems, and explicitly, they are artificial intelligence systems, right? So every artificial intelligence systems or expert systems are having the backbone as knowledge-based systems, right? So those applications, you have to be very careful when you implement your own system that would be driven by the knowledge base that we are going to see in the rest of the lecture series, right? And I'm coming over here to knowledge acquisition. Types of repositories, as I told, structured, semi-structured, and unstructured. Now, the inputs to the knowledge management system or to the knowledge-based system will be of these 3 types. One is structured. What is structured? You have a relational database system, you have a relational table, you have an XML data, you have an Excel sheet or a CSV file, or those are called structured data. You have a definite structure of the data. You are going to process that, and then you are going to acquire knowledge out of it. Now, this is where we have learned in data mining techniques, knowledge discovery techniques. They often deal with a structured form of repository, right? And a semi-structured is a text data. As I told you, reading a newspaper or reading an article, reading a research paper, reading a white paper. So whatever things that have text in it, a continuous form of high-level language in English or in Tamil or in Hindi or whatever language you have. So when you have a text on it, and when you read those texts and you acquire knowledge out of it, and that text input is called semi-structured repository. And unstructured is the audio file, the video file, the signals, and the sensor data from IoT devices. So all those are unstructured data or unstructured repository from which you have to pre-process that data, and then you go to your knowledge processing techniques, right? So these are the three main repositories on which knowledge base could take inputs from. And content parts model, as I told earlier, is parsing of this repositories to obtain, to capture, or to acquire knowledge to the knowledge base system. And knowledge representation. So knowledge representation is a formal model or formal representation of the knowledge that is being acquired, right? So there are n number of models, and every research group works on this particular process. This is very important if you're working in a knowledge-based system, or if you're going to work in an artificial intelligence systems, which is knowledge-based again, right? So these models are some of the oldest models. First order logic, if you're a mathematician, you would know what is FOL. And description language or description logic, this is one of the finest knowledge representation logic model, where you define logics, you define concepts, right? One of the best way to define your concepts. Say, for example, I'd like to quote one example. It's raining. This is the example, right? It's raining. Now, we have got raining is a verb, but then actually it is rain. When it captured the knowledge as rain, that is a concept. Rain is a concept. Now, how do I define rain? Our human brain knows what is rain all about, because we have been with that and we have learned through our experiences. But when I want to define that in a computer system, how do I define rain? So that challenge of definitions of these concepts, many concepts are being given in through the description language, right? And then we have petrinets and the frames, which are object-oriented data models, knowledge representation models, and working sets, working memory sets, and production systems are there. And there are so many customized models, right? And these customized models are mainly based on the applications you are going to use. Now, as far as we are concerned, me and Dr. Hepzibah, we have worked on a few projects, and we have defined and we have tailor-made some representation models, which Dr. Hepzibah will be talking at the later part of the presentation about the representation models, the customized representation models that we have used for our application. Similarly, you can use the same customized model, or you can tailor make your representation models, right? So we'll be seeing that in detail in a short while. And I would like to give a small example about the first order logic, right? Hope you know that, but then now I want to have a sentence like this. Right. Now, this is a higher level statement, higher level English statement. Now, this is an unstructured repository, unstructured data that I want to parse to acquire knowledge. Now, using FOL, how would I represent this? Right? FOL talks about logical symbols and functional symbols, and they talk about predicate symbols. Right? So here, I would like to define Raja as a rich man. So, rich man of Raja. Now note that this is a predicate symbol, so that I have given R in caps and M in caps. So whenever you talk about predicate symbols in FOU, you'll be having the capital letters and the small letters coming in. So this is a predicate symbol where this denotes the Raja, and this can also be a variable. This can be also a variable, so that I would have for all X or for there exists X. Now this is also possible in FOL. So there exists X, rich man of X, right? Now that is generalization. Now I'll go to the specifications. Raja, rich man is Raja, and I would define beautiful. Right, this is another representation. I'll call this as functional symbol. Functional symbols always start with normal case letters, and the intermediate one would be the caps, right? Now, how to differentiate between functional and predicate symbol? Functional symbols are often adjectives followed by the noun. So it's beautiful city. If you want to say just city, I'll just remove this. Now this becomes predicate. This is a predicate symbol now. Now this is a predicate statement. So when I want to have an adjective before that, then that becomes a function symbol. Rich man, I have taken purposefully as a predicate symbol. If I want to have, this would become a function symbol. All right, so now DL talks about, the description logic talks about defining this rich man and defining beautiful city. Now, when it comes to the definition, beautiful city is a city by itself. So first, I need to define city. So city will have a definition, some kind of definition like this. So in our other videos, I'll be sharing with you all the links of our videos. You can go through all the videos, and how to define classes are given there, right? So I'm just rushing off. So city has to be defined, and then it becomes a beautiful city. So I can have beautiful city is Muscat. This is a constant. This can be some other city also, right? So according to the given statement, rich man lives in beautiful city Muscat. According to this statement, I'm writing two FOLs, right? And when I want to combine this, two FOL terms or two FOL classes, when I want to combine this, rich man, and I put a conjunctive normal form, and then I'll say beautiful city. To be more precise, let it be like this, right? So rich man, Raja, and beautiful city. Now, where does this live? Now, how do I have this live? Live is a relationship. So what I have, I'll mark this as a predicate symbol and put it here, where P is a predicate symbol, is a relation that is defined as lives in. Now, this higher level language is represented as an FOL statement like this. So this is one form of representation of knowledge, right? Now rich man is a concept, beautiful city is a concept, and these things put together is called the knowledge unit. And their definitions are given, should be defined in using a description language, right? So this is a very simple example that I am quoting to you. Right, so till now, if you have any questions, maybe you can ask. Okay, so if there are no questions, I'll move on to playing the videos on, the video will be starting with knowledge reasoning. Now, assuming that we have learned knowledge representation, FOL representation, and we are going to knowledge reasoning, where we'll be dealing with some of important topics, which will give you an insight how to reason it out. And after reasoning, then I'll be playing the video of knowledge storage and retrieval by Dr. Hetziba, right? So let me go to. Okay, just I'm playing the video. Just let me know if the audio is audible, or if not, just tell me. Is the audio audible?
Yes, sir.
Yes, doctor. Yes, doctor.
Okay. Just I'm playing the video now. Just listen to the knowledge reasoning part of this series. This is the 4th lecture. Maybe I'll share the URL with you for the first 3 lectures also, right? Now, go ahead and listen to this. At the end of this video, I'll maybe if you have questions, you can ask me. And then we'll be going to the session 5, which will be about the implementation and the practice of knowledge-based design, right? And so here I'm playing. Please watch it. Hi everybody, welcome to the session 4 video series on knowledge engineering. In this video lecture, we'll be talking about how to reason out knowledge and build up the reasoning process using the knowledge that we have gathered or acquired in the earlier sessions. So we'll be covering about interpretation, denotation, satisfaction, terminological facts and the resolutions. In the earlier video lectures, we have seen about how to capture knowledge using content parts model and how to represent knowledge using some of the basic models. And one of the basic thing is first order logic. And when we're dealing with first order logic, we have been talking about syntax, semantics, and pragmatics. And the syntax, we have seen how to form an FOL statement, how to convert a higher level statement into an FOL statement. And here this interpretation, denotation, and satisfaction comes under the heading of semantics, which means you add meaning to your FOL statement. And the pragmatics part is the resolution. So how do you resolve a set of knowledge units that are in your knowledge base? And that comes under pragmatics. And a few terminological facts that we'll see how to process the knowledge units. Okay, interpretation. Now, when you have an FOL statement or an FOL term like a functional symbol or a predicate symbol, how do you interpret them so that it can carry meaning with it? How it can add semantic to that FOL statement? Interpretation definition goes like this. An interpretation of an FOL is a pair of D and I. The D is a domain and I is an interpretation mapping. So it is often denoted as tau equal to the pair of D and I. So, making it more plain, D is any non-empty set of objects called the domain of the interpretation. And I is a mapping called the interpretation mapping. Now the interpretation of the predicate symbol P belongs to one of these domains, D. So there can be n number of domains when you try to interpret a predicate symbol, and I being a mapping of the predicate symbol to the domain. Let's say, for example, I'll say my predicate symbol P is equal to dog. Now how would I interpret a dog? A dog can fall into any one of these domains. It can be a German Shepherd, it can be a Dalmatian, it can be an Alsatian, or it can be a Labrador. So it can fall into any of these domains, and I categorize these different varieties of dogs into these domains. So how do I interpret that? This is one interpretation. The other interpretation would be dog is a mammal. The other interpretation would be, say for example, D1 could be equal to a mammal, or D2 could be animal. So it goes on. I can have any number of domains in this set of D's, and I say the interpretation is dog belongs to a mammal set, or dog belongs to an animal set, and it goes on like that. So when you have an FOL symbol, a predicate symbol like this, or a functional symbol like this, before getting it added to your knowledge base, you have to interpret this predicate symbol or a functional symbol and add meaning to the statement that you have written. So the next one would be denotation. Now, assigning variables to the interpretation is called denotation. The example goes like this. Here is the functional symbol called best friend of Jim. Now, who is Jim? You may have various interpretation. When we had just a dog, when we had something like this, like you had dog of X. When you have X, this X means that you are assigning variables to this dog X, right? Similarly, when I write something like this, I'm not using a variable here, but I'm using a constant here, Jim. Now, how does this Jim get into the variable category? Who is Jim? Jim can belong to D1, D2 or D3 or any number of domains he would come up with, right? Jim can be a dog, Jim can be a person, or Jim can be a boy or a man, or Jim can be a book. So whatever constant you have given here, the same constant can be interpreted or denotated into a different set of domains from D1 to D2, D3, and they are all disjoint sets of domains. And ultimately, this Jim would belong to one domain according to this statement. So D turning to false or true. So the interpretation that we're given for Jim may be false or may be true according to the real world situation. Here, though Jim can be interpreted into D1, D2, D3, it ultimately belongs to only one domain according to the context of the statement given over here. So as we told earlier, your function symbol or predicate symbol is a term by itself. So I call this as T, and our interpretation tau over the variable assignment mu, right? So the function symbol acting on a set of terms together over a given tau and over an assigned variable is the denotation of the domains. You denotate the term to the domains, right? So the denotation is the interpretation of the function symbol f on the terms, and di is itself is a term with interpretation. So let me explain that. I say, for example, Jim belongs to a boy domain, or Jim belongs to a book domain, or Jim is a dog. So in either of these three cases, now boy is D1, book is D2, and dog is D3, and this DI, anyway, this DI has to be interpreted as a tau, another tau. So boy should already be interpreted, or a book should already be interpreted, and dog should already be interpreted and denotated as a term. So any of these domains that we have here is an already interpreted term or a predicate symbol. So only then this Jim carries meaning when it falls into any one of these categories. So that is what this statement means. Now the third one is satisfaction. More precisely, let S be a set of sentences and alpha any sentence. Now let us go to our old example, like cloud, sunshine. Let us take these two sentences, or basically these are terms, but we can call a term also a sentence when it can be defined and interpreted, right? These two form a set called S. So I'll write S is equal to, so here it says let S be a sentence, S be a set of sentences, and alpha any other sentence, which means alpha could be is equal to rain. Shall we? So keep this in mind. When we talk about S, we're talking about the cloud and the sunshine and the darkness and whatever. And when you talk about alpha, we'll call that as a rain. Now, the definition of satisfaction goes like this. We say that alpha is a logical sequence of S, which means that rain is a logical sequence of S. We have cloud and sunshine already in S, and now A and now alpha is logical sequence of S, or that S logically entails alpha, which means alpha is okay to be added to the set S if and only if
every interpretation tau on S is entailed. And then this interpretation also applies to rain. I'll put another way, if the interpretation of S is entailed, then the interpretation holds good for alpha also. So when I say S equal to cloud, sunshine, now I include rain also. Now I include rain also into the set because this rain alpha is getting satisfied in the interpretation that I already had. We have seen this example so many times. So I think that you would get this, this information right. So this rain has to get satisfied with the interpretation that is applied for this S. If and only if, then this can be added, this alpha could be added to the set of cloud and sunshine which is already in S. So when I have another class like that, say for example alpha 1, I'll say is equal to umbrella. If I want to add this umbrella to the set, then I should have a proper interpretation of umbrella which could be added to the S. So it's a logical sequence. It's a cloud, it's a sunshine, then you have a rain, and then you have an umbrella, then you have floods, you have then what, weather. So you can add n number of alphas to the already existing set only if this interpretation on S satisfies, and then this alpha of all the new alphas that comes in will be interpreted properly. So this is a satisfaction of an FOL statement that could be added to your knowledge base, yes. So finally, in other words, we'll say every model of S satisfies alpha. So it is a logical sequence that we are talking about, which will get finally satisfied with the alpha. And conclusively, you can logically say this also: if S and the union of negational alpha will be unsatisfiable. If only alpha is satisfiable, then we could add that into S. But if I take a union of the set S and negation of alpha, then this entire term would be unsatisfiable. So there is you have to be careful when you make a satisfaction derivation here. So ultimately we have seen interpretation, denotation, and satisfaction. If only these alphas, if only these classes that can go through interpretation, denotation, and satisfaction, they'll become valid so that they could be added into the knowledge base, and also at the same time they'll be valid for reasoning, to derive new concepts of new knowledge. Okay. Now what do I see in this figure is I have 3 blocks placed one above the other, and the top one is green, A is green, and the bottom one, C, is not green, and nothing is said about B. So how would I write this in an FOL form? So the main challenge here is that when you have a problem statement like this, you may have a problem statement in terms of a text, in terms of a higher level language that is spoken or something like that, and when it comes to figures like this, you should be able to interpret it properly and then write down the generalized form of the problem statement. So ultimately, when you get the generalized form of the problem statement, you'll be able to resolve this problem. So how do I go about writing this? Now this is my own interpretation. So I'll write something like this. I'll say on. On. On means what? Something is on. A block is on. On of A. If I write like this, what? On is a predicate symbol. So it carries two arities where A is on B. So if I want to interpret it in this way, A is on B. So the next one would be on B comma C. So which means B is on C. So on is a predicate symbol which needs to be interpreted and denoted. So I leave that to you, how to interpret this on predicate class, right? And then, okay, now can I write something like this? Green of A. And I can also write something like this. Negation green of C. So green is another predicate symbol which defines the color according to this statement. So green takes A. So A is green and C is not green. And I also can write B is also not green. B is also not green because the color of B is not given. So I'll take B is also not green, right? Okay, so here we have got two predicate classes. One is on, the other one is green. So it goes like this: on A comma B and on B comma C and green of A and green, negation green of C. So this best explains the FOL statement of this figure. So on A comma B, on B comma C, which means A is on B and B is on C. A is green and C is not green. Right? I want to add a new class C n plus 1 into my KB S. Now, how to do this? This is the most important part, and we have algorithms to implement this. So the definition goes like this: a resolution derivation of a class C from a set of classes S is a sequence of classes C1 to Cn. Say, for example, you always go with this statement, that is C1. C1 is the first class. C1 belongs to S. So assuming that C1 is already interpreted and it has satisfied the interpretation of the denotation, so it is already in S. So starting with C1 to Cn, where all of them are logically entitled to S, where the last class Cn is a C, which means it's an alpha, it's a new class, and where Ci, which means this C, the ith element, is either an element of S or a resolvent of two earlier classes in the derivation. Right? I think this definition is quite confusing. You'll be clear when you get into an example. Now, this resolvent is a new term that is being coming in. For example, say C1 is a class and C2 is a class, and these two resolve together to form a new class called C3. Right, which means, I'll come back to our example. This is cloudy. C1 is cloudy. C2 is no sunshine, which resolves to a third concept or a class called rain. Right? Now this is called a resolvent, which could be added to the class S if and only if this is interpreted properly according to the S interpretation, right? Similarly, you may also have something like this, C2 and the C4 and the C5. All of them can resolve together to form a new class called the C6. Now C6 is a resolvent which could be added to S, and which is resolved from the earlier classes that are available already in the S, right? So this is how the resolvents, the resolution techniques works, right? So this is a resolution procedure. It's an algorithm. You would want to go step by step. Input is a finite set S of a proportional classes, all the predicate and functional symbol classes. We'll just call them as classes. And output is satisfiable or unsatisfiable, right? Check if the S resolves to nothing. If S resolves to nothing. If S belongs to, check if a null set belongs to S, which means it resolves to a null set. Your resolution resolves to a null set and which belongs to S. Now this is going to be the end of your resolution procedure. So just to break out the loop, we are having this check, right? So if so, return unsatisfiable. Which is unsatisfiable? This would become the nulls would become unsatisfiable. So a null set cannot be added to your KB during a resolution procedure. Otherwise, check if there are two other classes in S such that they resolved to produce another class not already in S. As we've already seen, two classes C1 and C2 already in S resolve together to form C3, which is not already in S. Then that becomes your resolvent, and add that resolvent class to the S and go back to step 1. So if every other classes are getting resolved and you land up in a null set, then you break the resolution procedure and all the resolvents are already added to your knowledge base S. Okay, so this is an example I would like to explain to you. Toddler is a class C1 in S, and if toddler is a child is another statement, or this is a class C2 in S, and if a child and a male, then it's a boy. Infant is a child and female is a girl, and then girl, and then female. So all these 6 classes are already in S, right? Now how to resolve this and find what are these 6 classes talking about? Now, I would like to convert this into an CNF form, and it goes like this. So it is just a toddler, right? And the second one can be written like this: toddler, comma, child. So remember that the last one would be toddler. Okay, the last one would be the positive class and the others would be negated, right? And then the next class of CNF representation is child, male and boy. The next is CNF form is negation, infant, comma, child. The next is negation, child, comma, negation, female, comma, girl. And finally we have just female. So now these are the CNF representations of the given classes, right? Now once you are having this, you'll be able to resolve these things, right? Now how do we resolve the given 6 classes, which is converted into CNF form? And the resolution goes like this. You take toddler, the first one, and the second class, and then you resolve it, which means the positive literal and the negative literal cancels. Now these are called literals instead of classes now. Okay, so what is literal is an individual atomic class, right? So a toddler, this positive literal and the negative literal gets cancelled, and then you will be having child. And take the last one, the one before the last one, negation child, negation female and girl, and resolve this with the child. So this child and the negation child would resolve, and you will have female and girl, right? So you have this as a resolvent. So child is a resolvent, female girl is a resolvent. And then you go with the last literal female, and you will get a girl. Now until now the resolvents are added to the KB, right? Until then the resolvents are added to the KB. Until girl we have come. Now how to break this loop, how to discontinue the loop? So I include a negation of a girl, and then I come to a null set. This null set doesn't satisfy the interpretation of S. So at this point of time I'll have the loop broken here. So these three classes are being added to the KB. So you have got already 6 classes. It's 1, 2, 3, 4, 5, 6. So 6 classes you have got in your KB, and resolving these classes has given 3 more resolvent classes. So a total of 9 classes we have got into our KB now. There's also another negation of a query, negation of the last class, which we have got, but this is not added here, but this is used as a reservation to include in the future learning process, or in the future resolution process. So this is how our algorithm of resolution procedure works. Okay, let me stop here, and if you have any doubts in these things, this is a simple resolution procedure that the text talks about, how FOL concepts are being resolved to new concepts. Like we are taking the hybrid classes. How are we deriving into a hybrid class? And that is what is called a resolvent. Right, and so we'll continue with the next session if you don't have any doubts. Now we are going to see about the implementation of the knowledge base, and this will be taken over by Dr. Hepzibah. Okay, as time permits, we'll be talking about the representation, the customized representation models that we have defined for our application, and then what is about the knowledge base. How does the knowledge base look like actually? So we'll be discussing on these 2 topics, and I'll take another 30 minutes on that, and the rest of the time we'll be talking about the research perspectives in knowledge engineering area, right? So here I'm sharing my video. Just listen to the final session.
Hi all, welcome to the 5th video session of Knowledge Engineering series. In today's session, we are going to see the implementation part of KB, knowledge base. So I hope you might have seen the basic parts of KB, what is KB, what is KE, and the activities, the core activities, everything you might have seen in the previous videos. So directly I'm getting into the model selection. I hope you know what is knowledge representation. So in today's session, we are going to see the selection of knowledge representation models. You know what is a concept. If suppose we are going to make use of a simple concept or class that is not much coupled or connected with any other concepts, then the simple object-based representation is useful. Say for an example, let's take a simple class staff. and we are going to represent this staff D with the residential address. So it is just like your class with the attributes residential address needed for the residential address. So this is a simple class that can very well be represented with the help of object-based representation. On the other hand, if suppose I just want to represent the same staff with a skill set, then it is a concept-based class for which we need to have concept-based representation. See the diagram? Here we have the representation of a staff that is associated with the residential address, that is associated with the skill set and the family members. I have explained you the first two cases. If we are choosing the residential address, that is a normal object that can very well be represented with the help of object-based representation. For the second class, that is concept-based, for which we have to go for the other model. So we'll start with the object model, OSM, object structured model. A simple form of KU is represented with the help of OSM. The definition of OSM is given as it's a modeling environment for object-based ontology with knowledge acquisition, representation activities that is widely used for modeling, domain modeling, and for simple KU representation. This is a four-label structure. See, here we have a knowledge which is represented with the help of this four-label structure. That is nothing but C, S, F and A, where C is the representation of the classes. So class is a template that can be used to define an entity. Here we can very well take the knowledge as an entity that is going to be represented. So that is why it is going to be assumed or represented as a class. For the class, we need to have the attributes. Such attributes will be defining the class. So here we have given S as an attribute, which is nothing but a slot. Here we are going to define all the properties that is going to represent the knowledge as our class. In the class, we will be defining the attributes. Same way, for the knowledge, we are defining the attributes. Such attributes will be the properties of the knowledge. So that is the second label. The third label is F. F is a representation of facet. Facet is the constraints associated with the slots. So if suppose you just want to add some constraints for the properties or to the attributes, that could be very well represented with the help of F. Then we have one more attribute, the axiom attribute. The additional constraints we set for a relation. So this is the functional model of OSM. This is a pictorial representation. See, here we have concept that is with C. Then for the concept, we have associated relation. So each class will have a class name and its associated ID. For the class, we have slots, facets, axioms and references. References are relation with the other concepts or other classes. See, here we have slot. In the slot, we have two types. One is own slot. The second one is temporary slot. Own slots are nothing but the attributes we do declare inside the class itself to define the entity. Second one is temporary slot that we have seen in OOP. We will infer the attribute or we will derive the attribute from some other class. Same way, here also we have some other attributes that will be used to define this entity, but it will be off in the temporary mode. Here we have taken one example. John teaches music. This is the concept. This concept is going to be represented with the help of OSM. From this representation, we could extract explicit and implicit knowledge from this concept. This is the construct given for the concept. See, here we have the class name John teaches music. For each class name, we will have a class ID that is represented. For this construct, we have the concepts John from person. So person T is a class. For the class, John is the instance or John is an object. Same way, skill set is a class for which music is an instance. Same way, the relationship is also set over here. Teaches, knows, trains. John teaches music. So there, teaches is representing a relationship. Already I have told you, to represent a knowledge in OSM, we need to have some slots, facets and axioms. So the next one is slots. See, here we have person T. Person T is the class in which what are all the attributes we do have? Name, representation of the person, location, available, timing of that particular person. These are all the attributes defining the entity person. Same way, we have another class, skill set. For the class, what are all the slots we do have? Theory, instrument and experience. All such slots are the representation or the attributes for that particular classes. Next attribute is facets. Already have told you, facets are the additional constraints we set for the attributes. Say for an example, for the person, we do have one more attribute, available timings of. So it is a representation of the person whose available timing is. Same way, we have some more examples. The next one is axioms. Additional constraints we do have for the relationship. So skill set for which instruments, the additional constraints are the instruments contains or includes piano, violin and guitar only. Same way we have references. The references are teacher, artist and performer. Same way for music, classical music, Carnatic music and the other kinds. The next model is conceptual model. If suppose we do have two concrete concepts and such concepts are to be represented and they are conceptually related, then it needs higher order representation. So in such cases, we have to consider the data structure required to represent the symbol associated with the concepts, computational complexity to manipulate the data structure and the knowledge level entailments. Such properties are to be considered. So, considering all such things, we have taken conceptual graph as a prominent tool to represent the knowledge in this model. It's a paired structure with concept and referent. You know what is a concept? A referent has the links to the conceptually related knowledge units. The definition is given as the conceptual graph is a finite, connected, undirected, bipartite graph with nodes of one type called concepts and the nodes of other type called conceptual relations. These concepts are the node and the conceptual relations are the arcs in the conceptual graph. When you look at the conceptual graph, you know what is node and what is the arc. This concept can be an entity, event or an action. Every concept has its own attribute and such concept will be instantiated with instances like our classes and objects. This is the functional model of CSM, the pictorial representations. As we have seen for OSM, this is for CSM. Here we have concepts and relations. For the concepts, as we have seen, concept ID, concept type and referent type. Along with we have many metadata. Say for an example, concept content, descriptor, mapping type, referent pointer, quantifiers and designators. Same way for the relation, we do have relation name, relation ID and relation types. Same way here we do have another properties or another metadata, number of links, rules, associations for the links or relationship, arc set and link pointers. So, in order to instantiate this CSM model, we can very well make use of OR model, object relation model. What is the need of choosing OR model? OR model can be chosen because of its threefold functionality, which is the basic requirement for our functional model of CSM. See, that is given, that is represented. OR model is a threefold functionality like attribute, functions and relations. So hence it is a class as in OOP, but along with the class, the general attributes, we are adding the relation part. The relation part relates all the conceptually related classes together. Hence, the implementation of the concept is to represent it as a data structure and get stored in the relational DB. As we do give priority to the relationship in such model, we will make use of relational DB. This is the programmable syntax for CSM in OR modeling. See, again forms the structure of a CG. The OSM and CSM models have higher level schema representation and logical view of the KU, but the CFRM level representation, entailment level representation and knowledge level representation. See the interpretation. In the symbol level, we are going to make use of the logical symbol student. The non-logical symbols could be the subject pool or the collection of subjects. Same way, for the rules at the entailment level, we have option. Minimum option for 5 subjects, maximum option for 7 subjects. The function is selection from the subject pool. Same way, we set the relation and we do have the computations at the knowledge level. Student should be selecting the subject from the subject pool, and the subject pool should be offered from the program. Program is nothing but the courses. Same way, at the computation we have mapping, storage and retrieval of objects from the pools for every student. In the second representation, we are going to make use of for all x there exists x. I hope such things you might have seen in the FOL representations. Non-logical, we are making use of the functional symbol f of the subjects. And the rule, there exists x, q of f of s and r of f of s. This q and r are the representation of rule to select the minimum subjects and the maximum subjects. Same way, in the function level, we are going to make use of the predicate symbol p. There exists x, p of f of s1, s2 and till sn. Here p is a predicate symbol that represents the selection of the subject. At the knowledge level, we are going to make use of the predicate symbol t that represent the relation. So for all x, t of f of s1, s2 and sn dot t of p. So for the computation we have algorithms, procedures, complexity. The symbol representation, what I have told is given. You just go through the table. See, this is the structure of a 3-layer knowledge base. So we have design layer where we have concepts and facts, knowledge layer. So here we have the representations in OSM, CSM, CFRM model. Then we have storage layer. See, this design layer is associated with the repository. The repository could be either a structured repository or unstructured repository. Here the acquisition is taking place, and we have the knowledge layer. This knowledge layer is associated with the schemas, KU and KB definitions in frame sets and DL. The next one is storage layer. Here you have the connection with the different types of storage. Say for an example, either ORDB models or database storage model or cloud storage model. So we'll start with the design layer. The concept acquisition and the knowledge capturing or the logical entailments are confined to this layer. So already we have seen here we have interaction with the repository. Either that could be a structured repository or non-structured repository. From the repository, the acquisition will be taking place. So for the knowledge acquisition, we are making use of CPM model. CPM model is nothing but the content passing model. So concepts and facts are acquired from the repositories that are structured. If it is a structured repository, we will have databases, forms, templates, etc. Same way, the concepts and facts are acquired from the unstructured repository. So if it is an unstructured repository, we have docs, audio file, video file, images, tweets, etc. Representations of these acquired concepts are then done using FOL. Here we do make use of FOL for the representation of all these acquired concepts, either FOL or DL, resolving these concepts for their validity, entailing them to the set of classes, both atomic and dependent classes. Such activities will be taking place in design layer. So these tasks in this layer are completed and such concepts and facts are represented using FOL, that is done in the design layer. Same way we are resolving the things and at the end we are finding the resolutions. So all such concepts and facts and the resolutions should be created as KU either in OSM or in CSM models in the knowledge layer. So creation of KU is taking place with the help of OSM and CSM model in the knowledge layer. If suppose we do have abstract complex KUs, then we can very well go with CFRM representation models. Finally, the conceptual relation is the most important part of defining a KU and KB. We are establishing the relation, conceptual relation among the KUs or the KBs. That is the important phase, or that is the important part of defining a KU and K-ball. While we are prefetching the KUs and K-balls, that is bringing all the associated conceptually related nodes or conceptually related KUs. So we should be very much careful that the link we are setting or we are identifying the conceptual relation, that should be very much correct. So we'll go with one example. Man is an entity identified at the knowledge layer. All properties of a human or person is inherited as well its own property are required. Means we have an entity man. This man entity is having its own properties. Other than that, this man is inheriting the properties from human entity and person entity. Same way we have some predicates like son of, married to, works with, travel by, interested in hobbies. These are all the other predicates we are identifying for this entity man. All these are defined in frame set representation and DL description logic and ultimately codified into object relational data model class type. If it is ORDB model, then it will be of a class type. A function symbol will be in the format of OSM or CSM, which has the collection of OSM predicate symbols. All these things can well be defined as a class type in ORDB. We'll see. If it is a KB, here you have a representations will be in the form of. The last layer is the storage layer. Storage of all these objects can be done in different storage mechanisms like file storage, object-based storage and cloud storage. The object-based storage system is opted to be the better way to store, manage, retrieve these persistent objects of our knowledge base. So we are choosing object-based storage for its own characteristics. OBS, object-based storage architecture, is preferred for its collective advantages such as scalability, security, reliability and other non-functional attributes are very much good in OBS. So that is why OBS is very much good, preferred. Same way, cloud storage. Right now we can very well go with cloud storage also. Cloud storage is an extended platform for storage layer of the KBs. So, a concept that is acquired at the design layer gets transformed into a KB at the knowledge layer and which is getting transformed to a class type at the storage layer. This is the action taking place in the three-layer architecture. Design layer, knowledge layer and then storage layer. In the design layer, knowledge acquisition is taking place for which we are using the CPM model. We are identifying the concepts and the facts and we are representing such things with FOL and the other techniques. Second one is the acquired knowledge should be transformed to a KB for which we have OSM and CSM representation and CFRM2 for abstract classes. Then all the represented KU should be codified to a class type at the storage layer. Next we'll see the retrieval algorithm.
Okay, so hope you're getting in touch with the knowledge engineering concepts and the advanced concepts in that. I'm not able to play the rest of the video because many concepts are there, the storage and retrieval, and how do you implement all those things for knowledge-based building. Now, let me go into the research aspect of knowledge engineering. If you have any doubts till now, maybe you can ask professors, faculty.
Participants, if you have any doubt, you can ask the questions.
Okay, if I don't have questions now, I'll move on to the last presentation on the research and practice of knowledge engineering. So I'll be sharing my screen now. So whatever we have seen till now is all about the basics and the advanced concepts in knowledge engineering, right? So starting from capturing a knowledge and modeling a knowledge, representation and reasoning, and building them into a three-layered architecture, right? Into a three-layered KB. So a three-layered KB is all about doing all these processes. These components are not disconnected. They're all disconnected while we learn. But then when put into practice and building up a knowledge base, these components are to be there in your entire knowledge base process. Like I'll take an analogy like this. You take you consider RDBMS, like your MySQL or Oracle or something like that. Now, it is a complete package. It is a database management system which takes care of data, data formatting, SQL query, query engine, query optimization, triggers, events. So I can go on adding everything, locking, mutual exclusion, asset properties. So whatever we have learned or we have done in DBMS course, maybe if you have DBMS course, yeah, you'll be knowing all these things disjointly. But say, for example, a DBMS, Oracle, or a MySQL, you take any of these DBMS, all these concepts are there for us, and we are just an end user for the DBMS, right? We don't know how query is executed. We don't know how queries are optimized. When I have n number of joins, how my query is getting optimized, I don't know all those things. Because as an end user, I use the DBMS to my convenience, right? Similarly, knowledge base, building up of knowledge base carries all these components. The one that we have seen from capturing, from acquisition of knowledge to the storage and retrieval of knowledge, right? So everything comes as a single bundle when you put that into practice and building up of a knowledge base. So a knowledge base would be the major driving factor for a knowledge-based system. So we have developed at VIT, we have developed some of the knowledge-based systems, and we have got some success to some level because we don't have those kind of infrastructures. Like you see these IBMs and TCS and the big giants, they have all those infrastructures in buying supercomputers, their infrastructure, their cloud storage, and their retrieval algorithms. They have plenty of high computational infrastructure, but we as academicians, we are not into that kind of very great, very gigantic infrastructures. But then we have some servers in our campus, and we have our own clouds where we implement all these knowledge-based applications. So I'll be throwing some light on the possibilities of research where we can do. Right. So first we'll start with our education system. Like you and I, we are all working in education vertical. So we know all the process in education system. Like student coming into the college and student getting enrolled into a program, and he is registering for a course, and then he's attending classes, and then at the end he's evaluated for some marks, and then finally he's given a degree. So this is one of the complete process chain in our education system. So I call them as administrative data. Now you will have a management information system. We have a management information system in our campus at VIT Chennai. So they collect all data, they capture all data concerning a student. We are talking only about students now, right? So all this data are being captured in our campus using one or two tools, one or two MIS systems. Now, I just wanted to point to you about the magnitude of the data. Say, for example, a student is attending class every day 8 hours. So for one complete semester, he is attending what? 15 to 16 weeks of classes, right? There are 7,000 students in a campus, and there are more than 50 to 60 courses running only in computer science department. And you imagine the attendance data for a student and attendance data of all the students. 7,000 students attending, all of them, or not all of them are attending 40 classes, maybe 40 classes around the campus for a single day, 8 hours of working. Now imagine the amount of attendance data alone that I can capture in my MIS. That is really a big data. We have enormous data. Coming to evaluation part, imagine 7,000 students taking 6 evaluations in a semester. How many marks that you have? Sensitive data. Mark is a very sensitive data. So these are all administrative data. Every college will have an MIS, and every MIS will be having this much of volume of data. You call them as big data for sometimes. And most of the times, these data are remaining useless there. Until for that semester, when an attendance is calculated, those attendance are taken care, and after that it is put into junk. Once the degree is awarded or the semester results are out, the marks are put into junk. And we have large amount of data being put into junk for every semesters after semesters. See, for example, if an organization or an education institution is there for 20 years, like VIT, 30 years it is existing there, amount of data for the past 30 years is a huge data. It's a very huge data, right? Now, how, as knowledge engineer, how am I going to use those data? I can put my AI algorithms into those data, and I can put my machine learning algorithms into those data and get new insights. I take insights for decision making for my top level management, right? So now how do I do that? It is not only the MIS that does this. I want to have that as a knowledge base. So that's why I'm telling it should be from migration from MIS to KBS. So let all the tools that we have in our campuses, it is not just they collect data, put it in their database, process it, and move that to junk. This is not going to be the future, right? MIS has already been dead in foreign countries, right? In the West, in the UK and the US, they're no more having MIS, rather they're having expert systems that are knowledge driven. So think in terms of identifying ontology for your education system. So you need to construct a knowledge-based system, which will be functioning on an ontology. So every organization or any vertical, every vertical which will have its own ontological definitions. So VIT will be having some ontological definitions, and your institution will be having some ontological definitions. And there are some friends coming up from different universities and colleges. Every university will be having their own ontology, but the basic ontology would be like student, parent, faculty, top management. You have these basic structures. So when you are attempting to do research in this area, or when you're attempting to do practice KB construction in this area, you need to work on the definition of ontology, right? And once you have defined your ontology, then you define algorithms, acquisition algorithms, or knowledge discovery algorithms, or reasoning algorithms, so that your KB would be self-learning. Now, all this stuff that we see in Facebook and your online shopping, Amazon, and all this stuff are self-learning expert systems. Nobody's sitting there and typing, as you all know. Yes. Now, why don't we, or why can't we create a KBS, a knowledge-based system for our institution? So that nobody sits back in the database center and it write queries and take Excel sheets and ask you to do something. No, that need not happen when you go for a self-learning knowledge-based system. So if you're having idea about how to build up a knowledge base for my education institution where I have large amount of data, so I want to construct that data based on an ontology to a KB structure, and I design algorithms or I write algorithms for for enabling my KB to self-learn by itself. So when you have a KB that could self-learn by itself, then that becomes an intelligent system. That becomes an artificial intelligence system that would serve the community of students, serve the community of faculty, as well the top management. Right, so this is one throw of light on the education system. So this is how the architecture, maybe if you want, you can just grasp over it. The database, the traditional database that we have, and the knowledge acquisitions from the DB through CPM model that we have been discussing long back. And you have the representation model and reasoning model for your system, for your ontology, which will give you a knowledge graph, something like this. This is my own example where I have a knowledge hive. This is a knowledge hive kind of thing where I have students, faculty, exams, and attendance. Now, when we map this to the traditional database, I'll think the student has a student table, faculty has a faculty table. No, I'm not going to think as a table, not as a relation table in my knowledge base. It will be a knowledge unit. Student will be a knowledge unit where 7,000 students are attached to that knowledge unit, right? And then all the queries that are posted from the student or from the faculty or from anybody else to the knowledge graph would be given from the knowledge graph itself. So you need not go back to the database. You need not go back to your reasoning part. Rather, you have a knowledge-based structure where all the queries will be answered from the knowledge base itself. So you reduce the overhead of writing and calling the SQL queries to the database and coming back. So those computational overheads can be minimized when you go for a knowledge-based system. Now this knowledge base, these two components, K representation and reasoning, and the knowledge hive will work together in self-learning and getting all the knowledge that is required. The hybrid knowledge is added then and there when it is needed, right? So these are this will be serving as a query answering system for your institution, and as well you'll be having all the contents for your report making. So that is from the administrative part. Now coming to the teaching part of our education system. See, I lecture now. Now we have an audio of my lecture. We have videos of my lecture being recorded using Zoom. Then from that I can have my lecture notes, and it goes on like that. I can have quizzes, I can have evaluation forms like that. So our regular classroom will be having all of these stuff, right? Starting from a regular audio video lecture and all those evaluation patterns. It's a typical virtual classroom. Now, how do I convert this knowledge that I have in my unstructured repositories, in my unstructured file formats like audio, video, and lecture notes? Now, how do I convert them? Do I have a mechanism? Yes, we do have a mechanism. Now, if you're interested in practicing all those things, if you want to do research on this, you can go for audio processing and video processing. Now, all these days, these audio, video are converted to digital form, from analog to digital form. But here, I'm talking about convert the audio file into a knowledge form. That is quite challenging. That is one important research area where these days, the past 1 decade, what I've been talking to you in the earlier, from 2010 to till date, several researchers going on processing audio and video and text materials and converting them to knowledge units, right, into a knowledge form of knowledge form, right? So conversion of these repositories or of these type of content that we have is very challenging. That is one research area, research problem that you could focus on. The other one is suitable representation model for storage and retrieval. Now, as Dr. Hepzibah was talking about, she was talking about OSM, CSM, and the CFRM, right? They are all representation models designed for my application, for our application, right? Now, when you want to convert an audio component or an audio content into a knowledge form, what kind of representation model would be suitable for you? Maybe OSM and CSM may be suitable for you. If not, you want to have a separate or a new representation model, you can come up with your own tailor-made representation model. That is invention. That is your research, right? So you can write a paper on that. You say that I have processed the audio component, the content, and I have converted that into knowledge form. And I or my research team have come up with a new representation model to represent this audio video content. This is going to be our research. This is going to be your research if you want to do that. And I would like to mention this. Some 6 years or 7 years back, we did a research on music. So if some of you know about music, we have all those music language, right? That 5 lines and that black dots and white dots. These musicians look into that and they play their instruments or sing. So we have processed some repositories of those music notations, and we have represented that using OSM and CSM, right? So OSM, CSM are one standard model where some of the ontologies, I would not say all the ontologies, some of the ontologies would fit rightly into OSM and CSM model. And that research output have been published in some Scopus indexed paper, and that was presented in an international conference in Bangalore. So we came up with those representation models, right? And finally, and then the third point would be how do you share this knowledge that is being with you to your learners? How do you have knowledge visualization techniques? There are n number of knowledge visualization techniques these days, but not all of them are customizable, or not all of them are used by us, or not all of them will fit into our model. So in our case, we design our own knowledge graph. Google is talking about knowledge graph for their search engine, and we have designed some knowledge graph for our means, right? So knowledge visualization techniques, one of the important thing where your students would be getting impressed out of your classes, right? So this is the architecture for that, your classroom, your content in audio and the text form. Maybe I should include a video also here, right? So the final output is knowledge representation. You have a knowledge graph. So knowledge graph will be a visual form of showing your content to your students, right? And the next one would be healthcare. Healthcare is a very popular term across the world, across universities. Am I audible? Like someone is interrupting me? Okay. So healthcare is a very magic word where lots of dollars are pumped into this healthcare domain, and several research groups are working on this. Now, this is one simple, smallest part that we did at VIT. Professor Hema, I think she's in the session today. Professor Hema from VIT University is in the session. Professor Hema is connected today. Yeah. Professor Hema and me together did this work in this healthcare about ICD, International Classification of Diseases, version 10. There were numerous versions before this ICD in 6, 7, and 9, and now we are using version 10. And Hema came up with a very large classification of data. It is some 68,000 ICD codes. They call that as codes. Now, where these ICD codes are used? ICD code is, the structure of ICD code is something like this. It is a 7-digit code, which is used in the US hospitals, right? That is mainly used for insurance claiming for those who are admitted in the hospitals, right? So they use extensively. The American hospital systems extensively use this kind of coding to generate code for a disease that they would identify, right? So in our Indian scenario, we cannot use ICD code directly into our insurance system because our insurance systems hasn't come up with that idea. But then we can translate our electronic health system, EHR, into a knowledge unit, into a knowledge base, right? So you go to a hospital with any symptoms and you meet a doctor, the doctor would analyze, assess, and diagnose you with a disease or with any ailments, right? Now, the analyzed and diagnosed disease has to be given an ICD code like this. So this is S32.010A. This is happening in the US, right? And they send this code to the insurance company, and the insurance company would tell you that this is the amount of the insurance that can be claimed for this particular ICD code. Right, so this is what is happening in US, and what we are doing here is that we are converting this electronic health record, like it'll be your medical history. In layman terms, you call that as medical history, like, right? How many times I have visited a doctor, and what medicines have I taken, and what is my health condition? Your EHR have all those things. Now, what Professor Hema and we did is that we came up with a model where we have a central knowledge repository, a knowledge base, and a terminal knowledge base. Like your central knowledge base will be having all the ICD codes attached to a patient. Say, for example, a patient X is coming in, he will be having a certain number of ICD codes for which he is diagnosed, right? So the central KB will be having, regardless of your geographical locations, we propose this model for the whole of India, but then her research is on that area only, and this has to get approved through a patent, right? So when we implement that as a central KB, where a patient's information is available there, the patients can go anywhere across the country, and you meet a strange doctor and you say your employee code or your patient code, he or she will be able to take or extract the ICD code from the central KB and process that in their terminal KB. So the architecture is central KB and the terminal KB across the country, right? So this is one large research that we are doing, but we started with the ICD code. Maybe if you go to Google and find out ICD. ICD is actually proposed by WHO, World Health Organization. So it has 68,000 of codes that are there. It is a PDF file. And Professor Hema was trying to convert all those PDF files of data of those ICD codes into knowledge units. Now, the challenge here is that how would you come up with a generalized form for this 7-digit ICD code? So you need to have the explanation for all of these. So the explanations are given over here. So based on these explanations and based on these semantics of this ICD code, this is not just digits and letters combined together. They have semantics by itself. So when you happen to have your ICD code PDF file with you, maybe you can download it from the internet and find out what are they talking about. The classification of the disease is external or internal, or it's for male or it's for female, and the category, the severity of the disease. So all the semantics are added into the 7-digit ICD code. So this is a very great research, prospective research area where you can focus on. We started with this ICD code and we came up with a brilliant idea of having a central knowledge base and a terminal knowledge base. Maybe she has had a discussion with some of the hospitals in Chennai as well as in Kerala. And she has got success in that, in building up a terminal KB for these hospitals, right? So this is one area in healthcare. And newspaper, okay, we have discussed this earlier. I'm just skipping that. And the current research areas where the scope of knowledge base is more. So the first title I would give is IoT-based knowledge-driven systems. Now, these knowledge bases are rich with data, first of all. So now the sequence goes like this. They have data, you have information, and you process that information to have your knowledge, right? So data, information, and knowledge. Now, your IoT devices gives you only data. All those sensors from your IoT devices, maybe your Arduino board or your car or your refrigerator or your home security system, you name any IoT device, it's going to just give you a number of data. And I write algorithms for processing this data and convert that into information and later convert that into knowledge-based system, right? So this is one possible area where you have lots of data from your real-time devices. Now, what I was talking about education system is that they're all obsolete. It's not obsolete data. You have data which can be modified later also, right? Say a student is present in a class, you can change him if he's for absent. By mistake, the faculty would have given present. Or if a student is absent for a class and the later date he submits an assignment, and I change that absent into present. So those data could be changed when I talk about education system. But whereas here, an IoT device is running based on time. So all the data that are collected from real-time sensors are time-driven, and there are large amount of data which can be meaningful when you convert that into a database system, right? Of late, maybe a few months back, we did a research with one of our professors in electronics engineering. And what he was doing was like, I'll show you an example. Yeah, we did this work in alignment with that professor, Dr. Ghosh from Sense department. And it was like he's having a sensor in a furnace, in a chemical industry furnace, where it has a nitrogen gas. Now the sensor has to sense whether there's a leakage in the nitrogen gas in that entire chamber, right? When there's a leakage in the chamber, this sensor will identify and tell what's the density of the gas that's coming out of that chamber. So if it is less, it'll give an alarm. If it is more, it should give a different alarm. So we have tried to capture that data, and it is a continuous data, right? For the entire 24/7, it has to be a continuous data flowing into our database, and we processed that, and we came up with the knowledge model through which we are able to draw a graph and make a continuous decision out of that, right? So these are a number of data that we got from that sensor. And finally, we ended up drawing a graph against current, right? Volt against current. And yeah, that is one example. And we also plotted the data and the knowledge that is obtained from those sensors. I think they should be correct. Yeah. So these are kinds of works that we did for a real-time IoT sensor, right? And this is knowledge base again. Now those data collected are processed into a knowledge unit, and then they processed it. So that was a good work that we had of late. Maybe if you want to have such kind of work, you can throw light on it. And we have, as I told, knowledge base is the backbone of artificial intelligence, right? One example that we have worked with chatbot. We have implemented a chatbot, which is a knowledge graph. I told earlier, right? Knowledge visualization is very important when you go with the final end product. I talk about all the time about knowledge base, and ultimately when I don't give a good visualization about the knowledge that I have, then my works will be of no use, right? So every knowledge base system should be having a visual part. At the final end, the end user should be able to see what is happening. So chatbot is a common thing that you would have seen in all the organizations across the world and across all the applications, right? So we also tried to do a knowledge graph-based chatbot for VIT, and we call that as VitBot. So this is a simple thing, like you type something else, you type D, and an answer comes. Now, if I type like credits, right? So many answers for credit would come. Now, this seems to be a database-driven system. I put a keyword, you search a database and come up with answers. Now, actually, this is not. This is not a database system. This is a knowledge-based system, right? So when I type credit is the basic concept which we have designed as OSM, right? Using object structured language, OSM is defined. So every concept is defined as OSM for this chatbot, right? So wherever we have the concept as credit, everything is taken up, right? And if there are no answers found here, the student or the courier can write a query of his own or post a query of his own, which will be taken to the knowledge graph or to the knowledge base and processed, and this would be also added, right? And right, here's the knowledge base that we have. Now we are just displaying it for your visibility. Now I just want to modify. Now this is the knowledge. This is a linear knowledge graph that we have taken. See, total credits for this is one sentence. This is one FOL sentence, or I'll call this as one concept. This is one whole knowledge unit, right? So I can modify any of these nodes and find what happens. Say I want to modify this as 165, right? So I'm modifying a knowledge graph, a node in the knowledge graph, right? So the concept is saved to be as 165, right? So this is a visual representation of the knowledge graph on which the chatbot is being functioning, right? But the students or the end user will not know what is happening at the background. This is the admin part, right? Where we want to change the knowledge node, a provision is given for the admin, right? So this is one AI based. This is one example I'm giving. You can have a number of examples. I always use I always used to tell my students to create artificial intelligence applications when you work on your projects, even their final year projects or their regular projects. I'll ask them to do an artificial intelligence based applications. Don't talk about MIS now. It is all knowledge driven systems, right? And finally, knowledge based machine learning systems. Of late, maybe 2 months back during this lockdown period, me and one of our professor in our university, she belongs to machine learning research group, and I belong to knowledge engineering research group. So we did a combined study, and we are doing a machine learning model for the attendance system for our students. Again, repeat, we are learning, we are building up a knowledge learning model, a machine learning model for the knowledge based system for students attendance. We have MIS just to store attendance. No, it is not going to be the same now. Now I have converted that attendance system into a knowledge based system, and I apply my machine learning algorithms on that, and I predict how students would turn out to a professor. See, Justice is taking class from 10 o'clock in the morning. Now, how many have turned up to the class? In VIT, this is a fully flexible credit system. So a student can come to the class, may come to the class, or may not come to the class, right? Now, this is virtual mode. Now, my machine learning algorithm, my machine learning model has to tell this is a virtual class happening for faculty in Muscat, and how many faculty would turn up, or how many students would virtually turn up for the class. So my model on machine learning on the knowledge base has to tell me, give me an insight. At 10 o'clock in the morning, you'll be having 30 participants. You'll be having 120. So my
Dr. Justice, sir. Dr. Justice. Hello, sir. Can you hear me?
Yes, Mr. Kumar, we can hear you.
Yeah. So myself, Kumar Mohan, moderator of this webinar. On behalf of Sinas College of Technology, Oman, I thank Dr. Justice and Dr. Yasifa for this wonderful and knowledgeable session. Now I hand over the session to the participants who are willing to ask the questions. The participants can unmute and you can ask the questions to our resource speaker.
Sir, do you hear me? Dr. Justice, do you hear me? Hello?
Dr. Justice, sir?
Hello, Dr. Justice, do you hear me? Somebody is there? Mr. Kumar?
Yeah, Ram sir, I think he is not there. I'll check out.
He's not there?
I will just check with him. Maybe he has some technical. Yeah, Dr. Justice join now. Dr. Justice.
Dr. Justice, sir, here. Yeah, I think he has joined now. Dr. Justice, can you hear us? I think there is some technical issue.
Yeah, I'm in contact with Dr. Justice. He is trying to getting connected again. He has some issues.
Yeah, sorry everybody. I got disconnected out of the network. Okay. If you could have any questions posted, maybe.
Hello, doctor. Do you hear me?
Yeah, able to.
Okay, Dr. Just I'm Dr. Ram. I'm working in Shinas College. Doctor, you have explained something related to the knowledge representation and the basic knowledge representation that we have already have. That you have explained very well. Okay, I'm very much thankful for that. My question is, for example, I have collected some data from the website. Blindly, I have collected some data. Okay, so I have pre-processed it. Many pre-processing tools are available. You know it very well. So I have pre-processed it, and now I want to train this. Because most of the data nowadays, most of the data that we are planning to do it in a big data analysis model or something like artificial neural networks model, many new updations are coming for this one, or R-based analysis or NIME flows. I can use it in anywhere. But my question is, almost all these third-party application tools are giving out the accuracy level for around 60 to 70%, and that's not enough. That's not at all sufficient for preparing a proper knowledge representation while I'm processing a sensitive information. For example, I'm searching for an insensitive information. That accuracy level is not at all enough for me. So in such cases, how can I train the data after pre-processing? The pre-processing has been done. Okay, I can use some tools I have done. First of all, I have collected some facts. I have collected some data. I have pre-processed it. Now I want to train it. Can you suggest some method, or how can I perform this with high accuracy level? This representation. I mean this training.
Okay. Now, May I know what kind of data you're using? Like,
most of the
can you
time
give
series,
some example?
yeah, of course, time series based data. For example, I'm collecting some data related to weather forecasting.
Okay.
Can you tell me? It's of course it's a time series based. So how can I train it?
Okay. Now, training part is something different when it goes to machine learning language, machine learning models, right? Now, what we are talking about here is about the knowledge representation models. Now, when you have your data with you, the processing, the pre-processing step is towards your ontological semantics. Right now, you're talking about your testing and training data for a machine learning model. Now, we are not going to build up a machine learning model kind of thing. Now, what we are talking about here is building up a knowledge representation model for the data that I have. So when you have a weather-based data, a time series data, you have to model it for a knowledge unit based on the ontology that you have defined. So the first step is to define your ontology and then come up with a knowledge representation model. Now, do not confuse this model with machine learning models. So that is entirely different.
But for a proper prediction, I need, of course, this knowledge graph with a high accuracy knowledge graph. I need for a proper prediction level. For such type of prediction, of course, I need some regression or classification or whatever the models I'm using. Just leave it. Apart from the model type, what I'm using, I have to train this particular data. Then only exact knowledge representation graph I can get.
Okay. As far as I know, training the data here is not needed here, right? Because see, training and testing data for a model that you're built for your knowledge graph construction is different. And what we are going to do here is represent a model that would directly, based on the semantics, would have impact on your knowledge graph, right? Knowledge graph construction is mainly based on your knowledge reasoning. It's not about training your data. It's not about testing your data kind of thing, right? So our processing of data or our processing of information is mainly focused on the reasoning part of your knowledge that you have obtained or the data that you have got. So the challenge here is that you have to have a well-defined ontology. Based on that ontology, you go for deciding your knowledge representation structure. And based on that, you move on to the construction of knowledge graph. Whereas I understand, as far as I understand, you come up through the other way around, going through testing and training the data, and you build up your knowledge graph.
I have the query from K. Ram Kumar, Mr. Ram Kumar. The question is, how IoT-based data falls under unstructured data? Can you please elaborate? How IoT-based data falls under unstructured data?
Now, IoT-based data is not always unstructured, because when you get data from a sensor, that sensor is already defined. You capture a data from a sensor on a time basis, on a time series based data, then it is going to be a structured all the time, or sometimes it may be a semi-structured. When we talk about IoT-based unstructured data, it is about the audio signals or the analog signals of audio that would come in, or the video signals, right? So all those continuous data form is called unstructured data. But whereas when you get a censored data from a sensor device, then that is always going to be a structured or a semi-structured data, which is easy for processing.
Okay, I hope the answer has reached Mr. Ram Kumar. I have another query also from another participant. It is from Dr. Anuj PK. Can we say that faces are members of inherited or derived class? Can we say that faces are members of inherited or derived class?
Okay, that depends on your definition of your access specifiers. If you're going to give the access specifiers as public, then the slots and facets and the axioms will be inherited. That will be visible to the derived class also. Your slots, the attributes, as you do in your object-oriented programming, when you take it as a public, yes, it is always available. If you want if you want to hide the constraints, the additional axioms or the additional facets, if you want to hide that, put that under private. Yes, the inheritance properties of all your object-oriented programming applies over here in the OSM model. Yes.
Okay, there is another question from Sunita. Which tools are applicable for ontology other than Protege?
Protege is one of the powerful tools that I suggest that to be used. No, I don't find any other tool better than Protege for ontology definitions. So if you have Protege with you, yes, that could be the best tool for your ontology definitions. Go ahead with that.
Okay, thank you, sir. Is there any questions from the participants? You can ask Dr. Justice. You can unmute your mic and you can ask the question to Dr. Justice. I hope there is no more questions.
Yeah, see, we have a series of 5 videos in this category. If you are really interested in learning knowledge engineering, or if you are planning to take future courses for your students in knowledge engineering, I'll be sharing the links with Dr. Kumar or with Dr. Prasanna. Maybe you can go one by one at your leisure time. When you have time, you can go through all the videos one by one. We have given examples, all example-driven concepts are there. Maybe you can have a slow pace of learning, because 2 hours is not enough to bring out a good stuff to you all guys. So I think that we have made justice to the topic, and I'll be sharing the link with you.
Okay, we have the last question. It is from Babu Saab, ACT. Can you suggest any research ideas using knowledge, data, and IoT? He is asking for some ideas.
Okay.
Any research ideas using knowledge, data, and IoT?
Okay, so as I told that we had that problem that came from the electronics department, and we worked on that. That was IoT-driven sensor, IoT-driven knowledge base. Similarly, maybe I'm not so sure about where to get this IoT data, but then you can collaborate with other schools, maybe with other departments, your electronics departments or your electrical departments, and you can do a collaborative work where you get data from those IoT sensors and you process that as knowledge unit for your application. So to the most, I can suggest only that. As far as we are an academic circle, as far as we're an academic environment, we can do at the most to that level, where you can do an interdisciplinary or transdisciplinary research along with your colleagues in other departments. I would suggest that.
Okay, I think the answer has reached Mr. Babu Saab. It's a message to the participants. The feedback link is given in the chat box. You can start giving the feedback of this session. Dr. Prasanna?
Yeah, Ms. Shaija can take up. Ms. Shaija is there?
Yes, sir. Now over to Dr. Sudhakar for a vote of thanks.
Thank you, Dr. Seja. Respected Dean Dr. Ahmad Muhammad Al-Mamari, HOD Ms. Amina Salim Muhammad Al-Jabri, HAS of IT, Networking and Math Section, and all the participants, good afternoon. On the behalf of IT Department Research Committee, I extend my heartily vote of thanks to the honorable delegates who honored us with their presence and took out valuable time of your busy schedule. I must mention our deep sense of appreciation to our resource speaker, Dr. Justice and Dr. Hafsiba Mobile for their wonderful presentation. I also wish to express my gratitude to our HOD, Ms. Amina Salim Muhammad Al-Jabri, for providing supports and encouragement to organize this event. I would like to thank HUS of all sections, college administration, ETC, and all the friends present here in the webinar for their active participation and making this webinar a grand success. I extend my big thanks to our IT Department Research Committee for their support. My sincere thanks and appreciations to all the participants. Thank you guys for making this event successful with your contribution. Thank you all.